Hey everybody, in today's lesson, we are looking at a specific type of probability distribution called a binomial distribution that occurs a lot in many statistical applications. So let's dive right in with the little motivation problem. So many of you guys drive at this point in your lives, and maybe you've had this happen to you. But I know driving across Guelph, there's some stretches where you might have like 8 or 10 stoplights, and some days it just seems like you're hitting every red light, or maybe if you're having a good day, it seems like you're hitting every green light. Well, if you know how often the lights are red and how they're green, you can actually analyze the probability of hitting all red lights or green lights, or a combination of reds and greens. So that's what we're going to do in this problem. So here we go. On our drive to school, let's say you go through 10 traffic lights, and based on experience, the lights on our route are green 60% of the time and red 40% of the time. So what we're going to do is find the probability of hitting 8 green lights out of 10, but we're going to scaffold it a little bit. So to start off, let's talk about how many ways that you could hit exactly 8 green lights and 2 red lights. Because if we think about it, so I'm just going to write G, 8 greens and 2 reds. There's lots of ways that can happen. The 2 reds could be at the end. The 2 reds could be at the start. The 2 reds could be anywhere in between. So how many spots are there to choose for our 8 green lights? Well, in our organized counting unit, we would have done, so of our 10 lights, we're looking for 8 of them to be green. So there'd be 10 choose 8 ways to choose the green lights. If you used 10 factorial divided by 8 factorial, 2 factorial, remember that gives you the exact same thing as 10 choose 8. But we can do that quickly. 10 choose 8, 45 different ways that we can get 8 greens and 2 reds. Well, knowing that, let's keep going. What's the probability of getting 8 green lights in a row? Well, we can do this after our first unit. We have the tools to do this. So the probability of getting, I'll just say 8 green lights in a row. Well, the probability of getting 1 green light is 0.6, and getting a second, another 0.6, but there's 8 of them. So we could write that as 0.6 to the power of 8. And for now, I might just leave it as 0.6 to the power of 8. For C, the probability of getting 2 red lights in a row. Well, each red has a 40%, or each light has a 40% chance of being red. So 0.4 times 0.4, I'll write that as 0.4 squared. And then we can put these together. The probability of getting 8 green lights is 0.6 to the power of 8. The probability of getting 2 red lights is 0.4 to the power of 2. So the probability of getting 8 green lights and 2 red lights in a row would be the product of these two things. But we showed in part A, there's actually 45 ways to arrange these 8 greens and these 2 reds. So for part D, to put it all together, the probability of getting exactly 8 green and 2 red is this. We have 10 choose 8 ways to choose which ones are green. 0.6 to the power of 8 gives you the probability of getting 8 green lights, and 0.4 to the power of 2 gives you the probability of getting 2 reds. And you can calculate that all at once in your calculator instead of doing each individual calculation. We knew 10 choose 8 was 45 times 0.6 to the power of 8 plus 0.4 squared. So what we get is just going to double check that. I think I did something wrong there. I got a number that seemed really high. 10 choose 8 times 0.6 to the power of 8 times 0.4 squared. Yeah, that seems better. I got like 90%, which is definitely way too high. So here I got 0.1209 or 12.09%. So pretty low, but you know what? It kind of makes sense. You know, if the lights are only green 60% of the time, then getting 8 green lights, it's going to be pretty rare because we kind of expect to get 6 of the 10 green lights to be green. This kind of probability calculation happens so much where we kind of have a success or a failure, like a green light or a red light, that we give it its own name. And that's the topic of today's lesson. It's a binomial distribution. Before we go on to some definitions, can you use the previous method laid out here? If you'd like to do it just in one step, like so, that's okay too. But try this. We've done 8 green lights. What would the probability of getting 5 green lights be? Or 7 green lights be? So if you want to pause the video and try those, and unpause it when you're ready, or you can follow along with me right now. So what's the probability of getting exactly 5 green lights? So using the same method as last time, of our 10 lights, there's 10 choose 5 ways to pick which ones are green. The lights are green 60% of the time, and we have 5 green lights. And then if we have 5 green lights of 10, that means we're going to have 5 red lights out of our 10. And so this is the calculation that would get you the probability of getting 5 green lights, just putting it all together. Do that really quickly. A lot of stuff for today I've done ahead of time just to save some time in the video. Did not do these ahead of time though. So I got 0.2007 or 20.07%. The calculation for 7 green lights is fairly similar. So here we have to choose which of the 10 choose 7 ways to choose which lights are green. 7 green lights, so 0.6 to the power of 7, and then 3 red lights, so 0.4 to the power of 3. And let's see what we get here. 10 choose 7 times 0.6 to the power of 7 times 0.4 to the power of 3. 0.21, that rounds to 2.2150 or 21.5%. So yeah, this is a scenario, green light, red light, where you can kind of think of it as a success or a failure. The green light was a success and the red light was a failure. And in each time we had 10 traffic lights and we were looking for a certain number of those 10 to be a success, a green. This is an example of a binomial probability distribution. So it's a distribution with independent trials. So this is important. This idea of independent trials means your probability, if we think back to the traffic light example, means the probability of a success in each of these trials, or let's say traffic lights, is the same. You know, it's not 60% green one light and then 70% another light. If that changed, we couldn't do the calculations we did before. Every trial, every light had to have the same probability. And the outcomes are either success or failure. So in our example, a success was green and a failure was red. Any question we do today, there'll be 2 outcomes: success, failure. You're not more than 2 outcomes, just 2, success or failure. And in these questions, the random variable is the number of successes. So in our previous question, the random variable was like the number of green lights we had in a given number of trials. So let's put this into, let's take what we just described there, and then we're going to develop a kind of a formula to get the probability of any outcome in a probability distribution, and then try some examples. So just get rid of that little mark there. So in general, if you have n trials and you're looking for the probability of x successes, we write the probability this way. So the probability of x is equal to start off, we have a combinations calculation. N choose x. So the number of trials is n and probability x. So this gives you the number of ways to choose which of the trials are your successes. So it was like the 10 choose 5 or 10 choose 7, 10 choose 8 calculation we had with the traffic light example. It's number of ways to choose your successes times p to the power of x times q to the power of n minus x, where p is the probability of success and q is the probability of failure. So something you might want to get down is, this is always true. P plus Q is always equal to 1 because P is the success probability and Q is the failure probability. So like in the traffic light example, we had 0.6 for green, 0.4 for red, and those add to 1. So that's where this Q equals 1 minus P comes from. If P is probability of success, the probability of failure would have to be 1 minus that. Looking at each part of the formula, just maybe have just a quick blurb about it. So n choose x is like the number of ways to choose which of your trials will be successes. P to the power of x gives you the probability of having that many successes. And q times n minus x is your probability of getting all those failures. I might just add up here, n minus x is the number of failures. Like for the traffic light example, we had, for our very first example, we had n was equal to 10. When we were looking for the probability of getting 8 traffic lights, we used x was equal to 8. And then n minus x was equal to 10 minus 8. That was equal to 2, the number of failures, 8 greens and 2 reds. All of our calculations today will have the same format. Let's dive into some examples and get you guys some practice using this formula. So in our before we do that, there's actually a shortcut for finding expected value if your probability distribution is a binomial distribution. So normally we do the sum. So for our game show analysis and our 3-dice distribution, like normally we did expected value, we have to do the sum of all the outcomes times their probabilities. With the binomial distribution, you can do a shortcut, which is kind of nice. And it's the shortcut's the following. It's a little formula. You take the number of trials, n, and multiply it by the probability of success, p. So it's a really simple formula to use. For example, in our traffic light example, if we had 10 traffic lights and the chance of getting a green, a success, was 0.6, then our expected value would be 6 greens. So this is the key idea for this space there, but then this is just in a little example from earlier. Yeah, you can make use of that. You can still find expected value the old-fashioned way, but this is a nice little shortcut. All right, let's create a binomial distribution. Let's get some practice using the formula. And yeah, so we're going to consider tossing a coin 4 times. So where we're tossing a coin 4 times, that means the number of trials is 4. We're going to create a probability distribution for it. I should add clearly, we are going to find a distribution for the number of heads. We're going to make a table for all the possible outcomes and the probabilities, and we'll do some checks and calculate the expected value too. But if if we're tossing a coin and our success is to get the heads on that coin, the probability of success would be 0.5, which makes the probability of failure also 0.5. They have to add to 1. So in this case, the probability of P and Q are equal. So we might see some symmetry when we do a distribution a graph here. So I've given you guys a table, and I've done this work ahead of time. So if you would like to pause the video and try it on your own, or if you just want to continue on, that's fine. But to save some time, I've already done most of the work here. So to get probability to get 0 heads, so remember our formula was n choose x times p to the power of x times q to the power of n minus x. And each calculation follows that format. So for 0 heads, I have n, 4, choose 0, which is my x. P is my probability of success 0.5 to the power of 0, 0 successes. And then 0.5 was my Q, probability of failure, to the power of 4. And what you guys, I might just get a different color here and just make a little mention for you guys. These two exponents always add to n, right? 0 plus 4, because that's the number of successes and the number of failures. It has to add to the number of trials. So 0, 4, 1, 3, 2, 2, 3, 1, they all add up to 4. And I've got my 5 calculations here. There are 5 possibilities. You can get no heads, 1, 2, 3, or 4. It's never a bad idea when you're doing creating a distribution table to just make sure those probabilities add up to 1. So if you can do that as well. I've checked ahead of time. Those probabilities add to 1, so I know I'm in good shape. I didn't have to do any rounding for this question. If you did have to do some rounding, sometimes they might have to add up to like 0.9999 or 1.0001, but it should add to 1. And then I've got my expected value calculation going on the right. I gave you guys a column to do the outcome times probability to save you some work later. I graphed my distribution here. So I want to add a little note here. Since P was equal to Q, 0.5, then we had this, our graph was symmetric. We'll see what happens when P and Q aren't the same value in a few minutes. For your expected value calculation, if you add up those 5 products, outcome times probability, you get 2 heads. Or if you use the expected value formula, E at x equals n times P, we did 4 flips. There's a 0.5 chance of getting heads, gives you 2. So the expected value of heads when flipping 4 coins is 2, which actually makes a lot of sense, right? If you're flipping 4 coins, you expect half of them to be heads. And we got that 2 ways. We got that using our standard way, using the table, which was a bit of a grind. And we also have to use the shortcut, which is a lot better, really quick. But you guys showed there, it verified that it works. Let me ask you guys a question here. So here's a scenario. We have a probability experiment. So instead, we're going to draw 4 cards from a deck of 52. And I've said here that we are not replacing, so without replacement. And we count the number of red cards. So in this case, a success would be getting red, which means a failure would be getting black. So I've asked you here, why would this not give rise to a binomial distribution? So if you want to pause and think about that for a second and unpause when you're ready, but why would it not give rise to a binomial distribution? Well, it's because these trials are not independent. So if you think about the first draw, probability of getting red in the first draw, well, there's 26 red cards out of 52. So that is a half, or 0.5. But for the second draw, if you aren't replacing the cards, then the second draw, well, it could be the probability of getting red is different. Like if we drew a red card, there's 25 red cards left out of 51, but maybe you drew a black card, so there could be 26 red cards left out of 51. And we don't know which one it would be. So right away, our criteria for being a binomial distribution fails, because these are not independent trials. They're dependent trials, because the probability of success keeps changing. So that's important. You can only use the binomial distribution where you have the probability is the same over and over and over again. All right, so I'm going to have you guys try this one. I'm going to help you guys set this one up in a second. But so here we have a random number generator. So it's going to pick a number between 1 and 100 5 times. And we're going to say that repetition is okay. So it is possible to get, you know, like 10, 10, 10, 20, 20. It's possible for a number to repeat. We're going to calculate the probability distribution for the number of times a prime number is the output. So I'm going to help you guys out to get this one started. We actually have to know what how many prime numbers there are between 1 and 100. This could be a fun exercise for you if you would like to pause the video and give it a try. But let's actually just list all the primes. So 1 is actually not prime. 2 is the only even prime number. 2, 3, 5, 7. 9 is not. 11, 13, 17, 19. This is a good exercise for me, seeing if I don't mess this up. 23, 25, and 27 are not prime, but 29 is. 31, 37, 41, 43, 45 is not prime, 47. So I'm just going to double check. I did this one ahead of time just to make sure I didn't mess this up for you guys. 61 and 67. Prime numbers get fewer and farther between the larger you go. 71, 73, 75, and 77 are not. 79, 83, 89, and the only prime number in the 90s is 97. And if you count those up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So if our discrete random variable is the number of prime numbers, the number of primes, our P is 0.25. 25 out of the 100 are prime numbers. So you get a nice, decent value for P, which would make our value for Q 0.75. And here we are picking, randomly generating 5 numbers. So there's your P, there's your Q, there's your N. You have 6 possibilities, 0, 1, 2, 3, 4, or 5 prime numbers. So why don't you give this one a try? I've given you a table to do this. And then so you can pause the video, try those 6 calculations, keep 4 decimal places when you do your probabilities, and then unpause and you can check your answers with me. So here are my answers. So you can see the highest probability was to get only 1 prime number, which kind of makes sense if only 1/4 of numbers are prime. If you're drawing 5 random numbers, you only expect like 1 or 2 to be prime. So I got the highest number around 1, 0.3955. And you can double check these values add up to 1. They, again, because we had to do some rounding here, it may not be exactly 1, but it should be close to 1. And then I've got to just to make the expected value calculation using the formula easier, I've got my classic outcome times probability column. And when you add those up, you get pretty close to 1.25 prime numbers, which makes sense because 1/4 of 5 is exactly 1.25. Now, our graph in this case, because P and Q were not the same value, this graph is not symmetric. So when P doesn't equal Q, you're going to get a graph that skews to one side like this, and you can that the right one? 0.6. Oh, I plotted my x times p at x for that one. We got to fix this up right now. So 0.2373, that one was kind of okay. 0.3955, that was okay. Okay, but this one, 0.2638, that's a good catch. I don't want to have to shoot this whole video again. So that is way too high. It's 0.2638. 0.0879 is down here. 0.0146 is really low. And then the next one is super low. So start with that, guys. Our real graph should look like this. Might even get a different color just to make sure we all are on the same page as far as what the bar should look like. This one was okay. This one was okay. This one was okay. This one. Hey, this is just what happens when we're shooting lots of videos. Don't got a ton of time to like redo everything. But yeah, there we go. So that looks a lot better. And then our expected value calculation. Hey, do it the easy way with the binomial distribution. Expected values is n times p. We did 5 numbers. 25% are primes, 1.25. All right. We don't want to have to create a distribution table all the time. Sometimes just to answer a question, we don't need to make a whole table. We can just actually use our knowledge of the distribution in the formula. So that's what we're going to do here. So we have like a manufacturing, let's say we have a manufacturing plant here. They're making computer chips. So let's say the failure rate is 5% on some run. So 5% of chips are generally like defective. They don't work. So usually at a manufacturing plant for quality control, it's impossible to check, when you're producing thousands or millions of units, it's impossible to check each one. So often you'll have quality control inspectors taking a random sample and just taking a few here or there and testing those to get an idea of how things are going. So we're going to find the probability that more than 2 of them are defective. So more than 2, we're taking 30. So what we would have to do, well, there's 2 ways to do it. There's a long way, probably getting more than 2. So that's greater than 2 defective chips. So that would mean we could have 3 defective chips, or 4, or 5, or 6, all the way up to 30. So that would be like 28 different calculations we'd have to do. And none of us wants to do it that way. That would take a very long time. Instead, we can use the indirect method. Let's do it this way. The probability of getting greater than 2 defective chips would be 1 minus the probability of getting less than or equal to 2 defective chips. And that's a lot easier to do because that's getting, put a big square bracket here. That's no defective chips, 1 defective chip, or 2 defective chips. So if I use this method, I have 3 binomial distribution calculations to do compared to 28. So this is a lot better. So let me set this up with you guys and we can finish it off. So our N, we are testing 30 chips. Our P, so this is an interesting point. We are finding that probably that 2 of more are defective. So we're actually going to let our success be getting a defective chip. So sometimes students can have a hard time wrapping their minds around, well, how can a success be something that's defective? Like, it's just a matter of how you define it. Like back in our red light, green light example, we could have easily reframed the whole question looking at from the perspective of getting so many red lights. You can choose a negative thing to be your success. The probability of getting a defective chip was 0.05, which means the probability of getting a defective chip, 0.95. So I have 3 of those binomial calculations that look like this. So for 0 defective chips, 32 0 times 0.05 to the power of 0 times 0.95 to the power of 30 plus 32's 1. We're now on the 1 defective chip calculation times 0.05 to the power of 1 times 0.95 to the power of 29 plus 30 choose 2, 0.05 to the power of 2, 0.95 to the power of 28. And it's still a bit of work, but this calculation is a lot faster than doing 28 of these binomial distribution calculations. So I'm going to just slam this out now. You guys do it too, so you can pause the video, do this calculation, and see what you get, and then compare with me. "30 choose 2. Yeah, maybe this one would have been a good one to do ahead of time too. But as I said, time is limited. So I got about 0.8789 or 87.89% for that one. So if we think about it, let's just actually maybe do part B and then come back to this one. So part B, the expected number of defective chips. So using E at X equals NP, we've got 30 chips. P is 0.05. And so you're expecting 1.5 defective chips. So I think I just made a calculation error with this one. So yeah, forgive me guys. I'm just gonna recalculate this one. Working from home, do not have the time to reshoot a whole video or shoot even a practice video with my 3 kids hanging around. My 3 kids. I guess you can count my dog as a kid. So 0.95 to the power of 30 plus 30 times 0.05 times 0.95 to the power of 29 plus 30 choose 2 times 0.05 squared times 0.95 to the power of 28 equals. All right, so that is better. Matches what I got earlier. So I got 0.1878 or 18.78%, which fits a lot better because out of 30 chips, as we saw with the last calculation, we're expecting 1.5 of them to be defective. So to get 2 or more that are defective, it should be more unlikely than likely. So 18 or 19% seems pretty good. And we did, as you can see, having the formula is really good because if we didn't have the formula, you'd have to do all 31 calculations and do the X times P at X and add them all up, which could take a long time. So we did a lot in this lesson, guys. We looked at, we created a couple of different distributions in total in their graphs. We also did a few applications, and we learned a shortcut for finding expected value for binomial distributions. So next steps for you guys, my in-class should have their textbook, and the questions I have are from page 167. Or for my online group, I'll be making a handout with these questions as well. And you can give those guys a try. I also didn't mention this, but I'm going to have I'll have a short formative quiz on Brightspace as well for you guys to try. We have one more special type of distribution to look at in our next lesson, which I'll be posting in a couple of days. I want to give you guys a couple of days to work through this because it was kind of a big lesson. All right, guys, that's it. Thanks for being patient with the mistake or two, and stay healthy and have a great day. We'll see you guys soon.